Okay, so we start in English now. Today's TA will be about Markov chains. Just a brief reminder. The Markov chains are defined by the Markov property. That is that the future of the state will depend only on the present value of the state and not the past of the state. That's why here we are showing that the probability of going to the a future state given a present and the past is only dependent on the present. Basically, we are removing the past. That's the Markov property in simple terms. Mathematically, we can define a Markov chain as a stochastic process, x sub t, t is the time, where x sub t is defined on a finite state space S. So basically, we have finite number of states, and in each time step we do a transition between one state and other state with a probability, and the probability is this one here. This gives us a probability kernel, or a probability of transitioning from a state to the other. And in class you saw this vector pi. That is a row vector that denotes the probabilities of transitioning from one state to the other. And as you can see here, the future, or the state t plus 1, only depends on the state t, or that's the present. That's why this is applied in Markov chains. And the transition probability kernel is this matrix P. And each element of the matrix P is defined as transitioning to the state S sub j from the state S sub I. So the probability of transitioning from the state S sub I to the S sub j is this number, and that number goes to the element I j of this matrix. And that's basically all we needed to remember, and we'll start with the examples. As we did the last TA, I'll be doing the example because everyone is tired. It's the end of the semester, so I'll help a little bit. And for the first example, we have three states. The first state is snow, the second state is rain, and the third state is sunshine. And these arrows represent the transitions that are possible between states, and the number that is near the arrows are the probabilities of transitioning from one state to the other. For example, the probability of transitioning from the state 1 to the state 2 is given by this arrow and is 0.3. And if you want to go from the state 2 to the state 1, the probability is 0.1. You also have a probability of remaining or just staying in the same state all over and over again. And you have basically all the probabilities in the arrows. And basically what you need to do now is try to create this transition matrix P, and then we'll try to analyze what happens if I start with a vector of probabilities 1, 0, 0. That means that I start with a probability 1 in the snow state. And next we'll do a little program to find the probability vector in the state in the time step equals to 100. Okay, so let me just put a little screenshot so it's easier for us. here. Now, where's the image? Here. Okay, so we have the problem here. And now we start. First, I'll define, well, I already defined the numbering of the states. Let me plug my tablet there. Okay, so this is the state, whoops. The state 1. This is the state 2. This is the state 3. And let's create our matrix P that will have 3 by 3 elements. Okay. The rows are the current states S sub t, and the columns are the future of the states. And help me to fill this. For example, if I'm in the state 1, this is this one, which is the probability of transitioning to the state 1?
0.3.
0.3, right? So it's 0.3. And now, if I am in the state 1, which is the probability of going to the state 2?
0.3 also.
Also 0.3. And for the state 3, the transition from the state 1 to the state 3?
0.4.
0.4. Then, if I am in the state 2, that means rain, which is the probability of going to the state 1?
0.1.
0.1. Then, to go into the state 2?
0.45.
45. And then? This is also 0.45.
I really don't know.
So the state from going from the state 2 to the state 2 is 0.45, and from going to the rain to the sunshine is also 0.45. Now, for the state 3, which is the probability of going to the from the state 3 to the state 1, is 0.2. From going now from the state 3 to the state 2 is 0.3. And to go to the state 3 is 0.5. Okay, so that was easy. That was basically the answer of the question. We needed to find the matrix P. Now, which is the summation of the row entries of P? Let's see that. So basically, if we add all the elements of the row here, we have 0.3, 0.3, 0.4 that give us 1. You have this summation 0.5 that give us 1. And here give us 1. So always the summation of the probabilities needs to give us 1. But as you can see, if we do the summation in this direction, it will not give us 1. That's why it's important that to transition from one state to the other, we multiply by the probabilities as a row vector. That means from the left. So that will mean that we are multiplying by some probabilities of belonging to this state. Probability. Okay. Now, the second question within the first activity is what happens if we start with a probability vector of 1, 0, 0, 1. If you replace the vector 1, 0, 0, 1, 0, 0 here, and we do the matrix multiplication, what we'll obtain is basically the first row, 0 0.3, 0 0.3, 0 0.4. And that makes sense because we are starting in the snow state. So basically, all our transition probabilities are the same as this one, and this one. That are basically the ones in the first row. If we instead started from the rain state, our probabilities are this one, and this one. That are these ones here. And if we started from the sunshine, our transition probabilities would be these ones. So basically, that's why we do it as a row vector, because it makes more sense to do it like that when we generate the transition kernel. And if we put a state only with 1, 0, 0s, we'll retrieve only the corresponding row of the kernel. Is everything clear with that?
The last part I didn't understand very well.
What I was talking was, let me put that here, is here. Okay, so what I was talking was that if we started with a state that only have a 1 in the snow state, or we started with a vector state that only has a 1 in the second state, or we started with a vector like this that only has a 1 in the third state, and we calculated the I0 of P, in each case it will give us the first, the second, and the third row of the matrix. So here the solution that is 0 0.3, 0 0.3, 0 0.4. Here will give us 0 0.1, 0 0.45, 0 0.45, and here give us 0 0.2, 0 point something, 0.3, and 0 0.5. So basically what we are doing, if we put just a 1 in each state, we'll retrieve each row of the matrix of transitions. This is the matrix P, and that's what I meant by that.
Thank you.
Okay. Well, this was a easy example just to start, and now we need to calculate what pi 100 is. And how we do that? That is pi of 99 t, and that is pi of 98 t squared, so on. And we end up to just pi 0 and p elevated to 100. And instead of calculating this by hand, let's just use Python. So create another cell. Here. So we had our from numpy import array, our matrix B equals to array and our matrix was 0.3, 0.3, 0.4, 0.1, 0.45, 0.45, 0.2, 0.3, 0.5. That was our matrix, and our initial state pi 0 is equal to just 100. That's it. Let me check the shape of this first. Blah. And let's see what happens if I do this. Yep. So basically we retrieve the first column, and what happens if we do this but elevate it to 100? Well, that's weird. I'm not completely sure if it's doing the correct thing. Let me see. Yeah, it seems like it. Well, but that's it. Let me put just one. Yeah. And let me check something. Python matrix exponentiation. Oh, matrix power. Okay, so let's use this instead. From numpy linear algebra import matrix power. Matrix power E. Okay, so that makes more sense because whoops, my camera slide. That's better. Yeah, that makes more sense. Previously, it was doing the matrix instead of matrix multiplication, was doing a pointwise multiplication. By doing matrix power, is doing a matrix dot product 100 times, and that makes more sense because now the probabilities add up to 1. So this is pi 100, and obviously the probabilities needs to add up to 1. Well, 1.0002, but that's basically 1. Okay, so now we have the solution. Yeah. Whoops. Print pi 100. That's the probabilities in the time equals to 100. Okay, so the last part will be very related with the homework, and I'm not sure if we'll have time to solve it, but I'll explain at least a little bit of the problem. When we had the Lotka-Volterra equations, or the prey-predator equations, basically we had a differential equation. Let me see if I have it. Yeah, right here. So the Lotka-Volterra equations are basically these ones. Or let's show better the emoji equations because it's more clear. And we had the time or the rate of change of the prey and the predators depended on those terms here. Now we can also model that as a Markov chain, because I already told you that basically we had 4 terms. One that is related with the reproduction of the prey. Another one that is related with basically the predator eating the prey. And the death of the predator. And how can we model that? By these 3 terms in these 3 colors. So basically, if we have a state that has X preys and Y predators, how can we increase the number of preys by 1? And this is related with C1, that is the reproduction rate. Okay, so basically the reproduction rate depends on the number of individuals that we have. And also we have this cross term here that is the rate in which the predator eats the prey. This is C2. That's why it depends on the cross terms. And C3 is basically the rate in which the predator dies. So we have these 3 states that happened in the Lotka-Volterra equations. And as you can see, the rates or the probabilities of transitioning from one state to the other depend on the current state. And basically that's a Markov chain. And this is a little bit too small. Let me try to with 50%. That's a little bit better. Okay, so basically that's a Markov chain because the next state only depends on the current state. But previously we only saw the arrows with probabilities that remain the same over time. But now the rates or the probabilities of transitioning from one state to the other depend on the current state. That is the number of prey and the number of predators. So for example, if you have a population of X, Y, to transition to one prey more, this is related with the reproduction arrows these ones are the blue ones. And from here we can also go to this state that has a predator that died. That's why it's domained by the green arrows, because this is related with the death rate of the predators, and so on. And as you can see here, we can have cycles. And that's why in the Lotka-Volterra equations we had cycles as well. If you already solved the homework 5, you have already seen that the number of prey and predators are basically periodic, and that's explained by this kind of cycle that you can have here in the Markov representation of the problem. Well, and that's basically the Lotka-Volterra equations as a Markov chain. I'm not sure if you understood the model. In the next homework, basically the problem will be this one, the Lotka-Volterra equations with these different states. Victor, did you understand this Markov chain?
Some of them because I already see it, but not in this context. Also, I already use it as molecular phylogeny. So there's another interesting application of that principle.
Yeah. Well, when you try to model the generation of proteins, mRNA, DNA, and stuff like that, you can also model it as a Markov chain. And there's a algorithm that solves this kind of stuff that is called the
Hidden Markov chain, hidden Markov model in that case, because it used all the sequence alignments to produce and calculate the best probability to obtain a suitable phylogenetic tree.
Yes, in the case of DNA, you have some things that you cannot measure. That's why you call them hidden states. You have states that you cannot measure, basically.
Yeah, because in that case, because the codifying regions, codifying regions.
Yes. Esteban, did you understand this model?
Yes,
Yes.
it's clear.
Yeah. Okay. So the homework will be, I think, this problem. Basically, you'll do the same as the homework 5. You'll need to obtain the same plots, but with this perspective, and basically you need to generate the kernel, the transition probability kernel, but instead of depending only on a number like this one here, this number will depend on the state. So this p, instead of being constant, would be p of x, being x the state. And well, that's all I wanted to see in this TA, so there's no more doubts, so we can stop here.